Hey, welcome back everyone to our statistics class notes. We're now on page 125 in section 8.2 where we're talking about hypothesis testing. And we're trying to make sure we understand the p-value at this point. So as another example 147, according to nces.ed.gov, 24% of college enrollees were first-generation college students in 2002. So we want to know, let's say we're a researcher and we're interested in knowing if the current rate of first-generation college students has changed since 2002. So suppose that 75 out of 300 randomly sampled college students are first generation. Okay, so we want to know if it's changed since 2002. So the information we have from the past will be our null hypothesis. So H naught, or the null hypothesis, is P equals 0.24. That's what it was back in 2002. Then our alternative, what we're trying to see is that has it changed. Now change just means different. It doesn't mean it's greater than or less than, so we use the not equal sign in our alternative. So alternative hypothesis is P is not equal to 0.24. Okay, so this is what we're trying to see if our data is sufficient to say that the alternative is likely true. We want to know if we can reject the null and say we have enough statistical evidence to support the alternative. Okay, so this is a two-sided hypothesis because of the not equal sign. So it's not left or right one-sided. And this is the results that are given and displayed below. So I won't worry too much about it. I'll talk about it down here, how we get the z-score, but I want you to understand p-value mostly right now. So this is similar to the previous page. This is the exact same picture, as a matter of fact, on the previous page. So I really want to make sure you understand it. So we get a test statistic. If you look right down here, I compute it for you, and you can see how to do that one more time, of 0.4056. Okay, so that's right here. That's the z-score right here. Okay. Now, the probability of getting that test statistic or one more extreme would mean to the right of that. But since it's a two-tailed test, we also want the area to the left of minus 0.4056. In other words, we want the area in both tails, okay, because we don't care which side it ends up on. So that makes for a pretty big p-value here of 0.6851, and that z-score is not very surprising at all, right? It's only 0.4 standard deviations from the mean, so that's not a surprising test statistic anyways. So does that p-value of 0.6851 give us strong evidence to reject the null? Absolutely not, right? The p-value is bigger than alpha for any reasonable commonly chosen alpha, which are typically 0.01, 0.05, 0.10, etc. 0.05 is the most used alpha, but for the most part, it's not, this p-value is so big, it's bigger than any reasonable chosen one. Okay, so the p-value is the area in the tails. Again, it's the probability that your test statistic is what it was or more extreme, right? Further to the right and further to the left in both tails if it's a two-tailed test like this case. All right, and that's very interesting. It tells us, it gives us a way to measure the surprise, and we just measure it against alpha. So if p-value is bigger than alpha, we cannot reject HO, and that's what we got going on here.